Yeah, hello all. Welcome to week 10 live interactive session. So in this week, we primarily discuss about the epidemic modeling, which is we have already discussed the information diffusion, right? And so this is an part of that particular means it's related, but it's not exactly what exactly we have done in the information diffusion. So here we are discussing how the virus or any virus or any infection can be propagated in the network actually, right? So we have discussed that what is the exact difference between the information or action diffusion and any infection spreading in the network. So the infection spreading in the network, the main difference is that in the infection spreading there is a no choice actually, right? And in the information diffusion, that is in our hand, that is we have a choice that we need to that particular information we are getting from my friend or my connected user, that is up to me to grab that information or not. But in infection spreading or virus spreading in the network, in that we doesn't have the choice actually. So as we have gone through the that huge epidemic covid-19, in that there is a no choice in our hand. Suppose we are connected or we have physically uh, approach or physically connected to anyone, or we have approached any friend. So in that the virus has been influenced, virus has been um, attacked to that particular person or that connected user, right? There is a no as such the choice in our hand, right? So that is main difference we have saw mm, in the difference between the diffusion, information or action diffusion, or behavior diffusion, or in the mm, with comparative to the epidemic modeling actually. And also another thing we have, the difference is that suppose we have three friends, that three connected users are there, and in epidemic modeling we does not know which information has, which node has influenced or which node has infected me, right? That does not have information, so we require another modeling other than this information diffusion, that is an epidemic modeling, right? So that is overall summary what I have given, that has been covered in this week. Related to this, we will discuss some questions about that. And if you have any queries related to any concept about this epidemic modeling, so let me know in that case. Okay. Okay. So let's start by the first question. So in first question, states that assume for a disease C, there is an C named disease is there. Right? The people who are diagnosed in their earlier stage have a high chance of recovery. Right? Right. So those people has been diagnosed. Those people are already infected by particular that disease C. There is an high chances to get a recovery. Means earlier stage. So we have saw that is an in time period wise the disease get infected actually. So those who has got the infection in the earlier stage, earlier time step, then there is a high chances to recover that particular users, right? So the second sentence in this question states that the recovered people do not have a chance to get infected again, right? If they have already infected, then they recovered from that particular virus C, and after recovering there is a does not have any chance to get again infected by disease C, right? So what kind of model does this disease C exhibit? So this is very simple. What do you think, which model this disease has been conducted? Anyone? So we have saw two models in epidemic modeling. That is actually three models. That is, first is a basic benching model. That is, there is a tree structure, right? And second one is an susceptible SIR model, which is susceptible infected and recovery model. And third one, which is an SIS model, which is an susceptible infected and again susceptible. So out of these three, what do you think that which model is best suitable for this disease spreading that has been described in question one? Anyone? Let's let's go by one these options. So SIS means that is susceptible and infected, then again susceptible, right? So the node gets firstly having it colors. Node get first susceptible, then means there is an chance to get infected. That susceptible means, right? And then if it is if it is contacted with any connected person, connected, there is an friends of this particular user, right? And there is an connections, direct connections of these users, and he is infected by any particular by his direct connection, then he will get as an infected, right? He will get as an infected. That is an right. So after infection means this infection, like let's take as an that cold disease maybe, right? So that cold disease, again and again we are infected by that cold disease. Means suppose we are contacted with any person, any friend which who has an cold, so there is an higher chances to get that me also, or that particular user is also infected to a cold disease, right? So after a few 2 3 days taking a medicine of that particular cold disease, that user is also get recovered, right? And there is again chance to get that particular user is an infected by a cold disease. There is as such criteria, or as such situations are there that suppose if you have infected by a cold disease at one time, then there is also another chance, means after some days or after 1 month you will get as an cold disease again, right? So this is an susceptible, infected and susceptible. This is the disease exhibit like this way actually, right? So there is a no like that state that I have already explained. That is, an if that node is infected after recovered, there is also chance to get as an that particular user as an infected, right? Again and again, right? So this process goes again and again. So in SIR model, so that is an susceptible, infected and recovery. So recovery in this, what exactly there is an flu or any virus. So those virus, suppose if infected to you, then there is an after taking medicine, after few days, after some certain period of time, that person, particular person gets recovered, right? And there is a some flus or viruses, they will not infected again. If you are if that virus is infected once in your life, then there is a no chance to get that particular virus again, because your immunity gets stronger to tackle that particular uh, to address that or tackle that particular virus actually. Okay, so that, so how the process goes actually. So the once there is first there is chance to get a person that is an infection, right? Right now the user is not infected. Let's take as another color. So let's take a green. So this is in this the green color shows that this node is an uh, able to or get chance to get infected a particular virus actually, right? So right now that particular user, this user U1, it's not infected by any virus or flu. So after he's contacted with any person, so he gets. So this is transaction I'm showing here, how this user transaction from one state to another state. So then he contacted with any person, then he has get infected a particular virus, right? So that is an user U1, but it is an infected, infected by user. After taking the medicine, then user gets recovered. This user gets recovered, right? So after recovered, there is no chance, there does not have a chance to get again this node particular infected. So this is how SIR model implements or process actually. So as compared to our question, that question states that the disease C will be diagnosed earlier stage. The people who are diagnosed in the earlier stage have high chances to recover, right? The reason chances means there's in previous times, and there is suppose 10 days are there, right? In the first day who people are infected, there is high chances to get recovered in 10th days, right? Likewise the statement has stated there. So the second sentence, which states that the recovered people who has recovered that particular virus, that does not have a chance to get again infected particular disease C, right? So this express this SIR model, right? So that's why here the option is SIR model is SIR is correct, because uh, this is how SIR is implemented. As described, this is how the disease is infected and recovered, and based on that, the SIR is best suitable to implement this or model this epidemic problem, right? Yeah. Is there any doubt or any difficult to understand anything? Let me know. I will repeat that and we'll discuss on that. Yeah, if not, we'll just jump on next question. So, yeah. So in this question, the two statement has been given. We need to choose which one is correct. Right? So the first statement states that SIR model should come to an end after running for a running for a finite number of steps on a network, right? So it is stating that SR model gets terminate after some finite number of steps on a network. And statement 2 states that SIS model, which is an susceptible infected and susceptible model, can keep running indefinitely on a network. So what do you think that which statement is correct? Yes. Anyone? Right. Let's take one graph and understand how the exactly SIR and SIS model implements. Right. So the reason, as we have stated, this SIR model and SIS model implements based on the time period. At time period T1 means at day one, at T1 is equal to day one. At day one, the user one is infected. So here, let's take uh, this user is get infected at t is equal to day one, right? So only this one is infected. And at day one, and at the end of the day one, it gets recovered actually, right? It gets recovered. So all these black nodes represents these nodes are those nodes are susceptible. They are not infected till now. Okay, and the red node here represents the this that node particularly particular node is infected by disease or any virus. Okay, and at the end of the day, at the end of the day, this that infected node gets recovered. Right. So at day one, that this particular node gets infected itself, and he has that particular node infected their friends as well. So he it is infected by this node, right? This node, and then this node gets recovered because sorry, I will take another one. So this good node is get recovered, right? So now this node is an infected, right? So at t1 this is at t1, this is at t2, and at the end of the t2 it gets an recovered, like likewise it at t3 it gets recovered to infected to this node, right? Let's take as in 2 days actually. Okay, so at day one it is infected by itself, and day two it is infected to another person. At the end of the day two it is recovered the first node, this user one, right? Likewise, so at day one it is infected itself, right? And day two it is infected to this node, right? And end of this, at the end of this day node it gets as an record, likewise. So if it is recovered, then it is goes to the locked state. Locked state. Locked states means the that particular node is not get again the again infected, right? So this is how SIR model implements. Okay, so after suppose this node gets infected at a certain period of time. At that time, this node can't able to infect this node because it is already recovered from that particular disease. See, this node only infects this node only because it is in susceptible mode, right? These are the infected, those are the locked, we can say those node we can remove from the network, or those are locked, they are not able to record again. So this is how SIR model record. So at after certain period of time, this implements again and again and again, and after at some point of time, all we are getting the all nodes as an recovered, or all nodes are susceptible. There are two networks we are getting after implementing, after modeling the SIR model, right? So this is the one condition, one state, that is, and all the nodes gets recovered. So this is one way we are getting the output of the SIR model at the end after some finite number of steps, right? And after getting the all the nodes has an recovered, then our SIR model terminate there. That means the SIR model ends there. So the configuration we are getting this one, or we are getting only the nodes are susceptible, that there is no users are infected in this network. So these two possible cases we are getting from the SI, and at this state of the graph, uh, the SI model terminates. So this is the statement one states actually, that is an correct statement, right? So at certain definite after finite number of steps, our SIR model or any SIR model on any disease gets terminate, gets end. Let's see the statement two, yes, which is an SIS model can keep running and indefinite. So it is incorrect or not correct. Let's understand firstly how SIS works. So I will draw here. SIS model, right? So let's take as the same example, or the graph. It's a random graph I'm drawing here, right? Then let's start from the node one. Uh, this node one gets infected, right? Then it is infected at time t1. Time t2 means day 2, it infected to their friend actually. So it can either infected this node or this node as well. Okay, based on the based on the choice actually, based on the that already said, the each age has a probability, and means how much what is the probability to get this node infected by this node, right? So that is probability. Based on that probability, this the nodes gets. Now I'm taking randomly the this particular node is infected like this way, right? After the day 2, after the day 2, after the, so one second. So this is an day 1, this gets as an day 2, and at the end of the day 2, this particular first node gets as an recovered. Recovered means it's recovered and it falls into the susceptible mode. So all this, here is the, this is in now susceptible mode, right? It's not an recovered actually, it is an, again suppose it is an recovered from particular cold disease, then again it is chances to that particular person gets again cold disease, right? So that's why it again goes to a again goes to a susceptible mode, right? So then d2, in d2 this node gets infected. After that, this node at d3, day 3, nodes get infected, and at the end of the day 3, this node again goes to a susceptible mode. So now you are observing here, the nodes are getting the susceptible and gets infected, and then after infection, after some taking medicines or any therapy, then gets that particular nodes again in susceptible mode. So this process goes on. So this day 3, this node can also infect to this node as well in day 4. There is also chance to get to get this node as an infected by this node, right? At day 4, at day 4, right? So likewise this node, this process goes on. So it is an not stoppage criteria as there actually. So it implements or it runs, it models infinite time. There is a no definite time step to get this all the network gets as an uh, disease free actually. So you can see as let's take as a real life network actually. Suppose we have a network, we have a network means we have a friends, means let's take our node, that is an 2 3 students are there, and those 3 students there as an their friends are there, right? So those friends there as a families are there, their families friends are there, likewise this network is constructed, right? They are communicating, means they are regularly communicating to each other by physically mode. So there is a connection is established in between the nodes. Node represents the person here. So in this real world network, okay, so there is an, suppose let's say an cold disease. So cold disease, in this cold disease, if this node is infected, and then if it is contacted with that particular person, this person, then this node is also infected, right? After some period of time, this node is gets recovered, right? After some point of period of time, this node gets recovered, but he has already infected this person, this person, this person as well, maybe, right? And there is after certain period of time there is also chance to get this node again as an cold disease, right? In our real life also, we has infected many times in the cold disease. If there is an by environment change, that is a one reason behind that also. And then is another thing, that is an if we contacted or we have connected with any person which has an who has an cold disease already, right? So that's why this modeling, that is an SIS, it goes indefinite time, right? So that statement states that, second statement, SIM model can keep running indefinite time, indefinitely on the network, right? So the here the both the statements are correct. Both the statements are correct, right? Yeah, let's move to the third question. Consider a tree network. Yeah. Tree network to demonstrate transmission. Infection transmission means someone has infected, someone gets infection. Likewise, if one node has an k children each, and the probability of transmitting an infection is p, then the number of secondary infection is. So the question is asking about how many number of infected, how many expected number of users gets infected in the secondary infection, in second level of the tree. I will explain the question in detail, so that you can understand the question easily, and then you can give the answers. So it states that the network is a tree network, right? So the tree, we know that how the tree represents, and each node has k number of childrens. So there is an 2 means k, we have considered in this graph, which is an k is equal to 2. K is equal to 2. Okay. So it is stating that that each age has some probability p. Probability, what is an probability? That is an what is the probability to infect this particular node to this node? What is the probability to get this node is an infected by this node, right? So each age has an probability p. So here in this scenario, in the tree network, they have given that each age has a same probability, right? There is no like that this age has an zero point 0.3 and this age has 0.4. All the ages, whatever the probability, zero point 0.3, if it is zero point 0.3, then all the ages has an 0.3 probability. Okay. So likewise, the probability is there. So considering this tree structure, tree network, which has each node has an k number of childrens, right? And there is an also given the probability of transmitting an infection from one node to, right, upper node to lower node is an p. Then what is a secondary infection? So let's consider only this part. Okay. So we have a node which has a probability p, and there is a two nodes. So considering this, we need to find number of secondary infections. Means at this level, how many users gets infected? There might be a zero node, means no one has infected. There might be one node only, out of two, one node is infected, and there isn't, both of the two nodes has been infected. The three cases are possible in this scenario, right? So I have taken k is equal to 2. That's why there are three cases are there, right? Means suppose if you are taking the k is equal to 10, there are 9 cases are there, right? Likewise. Okay. So considering this, let's find how many expected number of uh, users get infected in a secondary infection, in we are calling an secondary infection. So as we saw in that is an reproductive number that we have saw, right? That is an, suppose this node get infected by, that is an, by using the probability p, right? Or another, this node is infected by getting a probability p, right? Right, so we have a probability 2 is 2 into p. So this is the probability to get this many nodes as an mm, number of nodes gets as an infected actually. So that we have seen one that what r0, that is an reproductive number that we have seen in the uh, lecture actually, that is already proved and already explained in detail how this formula got means evaluated, right? So that reproductive number, how we are calculated, that is represented a secondary infections, how many users get infected in second level, means the level of the uh, that particular level of the tree. So this will be works for the binary, means what we can say, the branching tree. This is a branching model actually we are calling, that will be implemented on the tree network. So here how the reproductive number is calculated, that is k into probability p. So here you can see the 2, let's take, and suppose the probability we have as in 1 divided by 2, that is a point 0.5 point 0.5, right? Point 0.5 probability to gets the particular node. So divided by 2, then we are getting 1. So r0 is equal to 1. That means out of these two, there is a higher chances, or one at most one node gets as an infected. So this is how we are calculating the secondary infections, right? That we have saw in detail. So already in the explanation we have discussed the example, this discussed the answer actually. So you can see the p into k, that is exactly the equation, or that formulation we are using to find the number of expected users to be to get sign infected. Right? Yeah, I hope this has been understood. Is there any doubts? Anyone? Suppose we wanted, right now there might be one question in your mind that you have found or you have calculated in this level 1, this is an level 0 of the tree, level 1 of this tree, and level 2 of this tree, right? You have calculated the number of expected, how many users get infected, that you have found in this level. So what could be what is the possible infected user in this level 3, level 2, that is, this is level 1, this is level 2. So for that we have saw, that means that is simple assumption we have drawn there actually, that is an expectation we have calculated, how the expectation we have calculated, that is an, suppose expectation to get, this is an u1, u2, u0, right? So for this level, so I will give a little hint actually how the this equation derived. Let's try to find how it is evaluated. So we want the expected this expectation of this gets node, this u1 user u1 gets infected, that is the expectation of user gets as an infected, the expected of user u2 gets infected likewise. Okay. So expected, how it is can this node is infected by using this probability, right? If that particular node gets as in this probability, if suppose there is an probability p is equal to zero point 0.5, so let's take a coin and let's toss a coin, and then we suppose the probability, if we got as an head, then we are infected that particular person, like this way. Okay, so this is a random process we have assumed, actually means that is an actual random process, but this is how we are understanding actually, that dropping a or tossing a coin, and then if it is that is fair coin, and if it is head, and then that particular node is get infected. If it is an tail, then that particular node is an not infected, likewise. So here, if it is infected, then which how much it is infected, how means by what probability it get infected, that is in P. Right? So U2, how much probability it gets infected, it is in P. So here we are getting as a 2 into P. Right? And here, why the 2 we get, suppose it has an right now we have two nodes. There might be k is equal to 10 nodes, or k is equal to 5. Then each node has children as in 10 nodes, right? So there is an up to 10, e10 is equal to u10 we have. So this might be, in that case, this might be 10 into P, right? So this is how we are getting this 2 represents as an k into P probability, which represents a number of users gets expected number of users gets infected at that particular. So this is we found for the level 1, and for the level 2, how we are finding for the k users, this is the expected numbers. So in level 2, you can observe that how many children users are there. So for this k users, there is an k childrens are there. See, for each user there is an k children, for each user for k childrens are there, so up to k. So I hope you understood that means what I am saying. So if we have 1 2 3 up to k, and for each node has an k children's, likewise. So the total we have k square users, right? So in that case, so for each k we have a probability, actually means for each node we are finding how much for this tree subtree, how much gets infected, that is an p into k. So p into k up to k square, that is in p k square. This is for the level 3. For level, this is for level 2, this for level 3 it is an p into k raised to 3. So likewise, the expected number of infected users can be calculated. Okay, there isn't too much. So the answer here. Yeah, let's jump to the question 4. Suppose the basic reproductive number is estimated to be R0. So now we have discussed the reproductive number, basic reproductive. What is an basic reproductive number? Which is an uh, secondary infection numbers, right? So how many gets infected? If it is that particular number, reproductive number is less than 0, less than 1, that means there is a no one gets infected. So this is not an epidemic modeling, means they are not epidemic is happening there, right? Because there is no one infected, then there is a no infection has been propagated or spread on the network, right? So okay, let's come to the question. Basic reproductive number is estimated to R0, which is an 2.5, a vaccine providing a certain level of immunity. So they have uh, provided a vaccine which provides a certain level of immunity is introduced. Okay. And the new reproductive number is found to be, that is an R1, represented as an R1, which is an 1.8. What is the percentage of immunity provided by the vaccine? Are you getting? So in the initial network, they state that they calculated a estimated number of users gets infected by using a basic reproductive number, that represents number. So how that particular number we are getting, that is an probability into number of children's, number of that particular tree has an uh, trees children's are there, right? So likewise, so so how this is, how it is calculated, that is an k into probability, like that. So r0 here it is given as an 0.5, right? If this r0 less than equal to less than 0, then there is a no uh, epidemic, or epidemic spread is happen, means there is a no spreading is been has been done actually. So so that is an the spread or infection died away, right? So that is a probability of died away is equal to 1 in this case, and infection died away is 1, right? And the r0 greater than, sorry, it is n 1, this is n 1, okay, it's greater than 1, then probability of infection persist in the network which is greater than 0. Okay, there is some chance, it's not exactly equal to 1, but there is some chances to the virus or disease has persist in the network, right? So this is one assumption that we have studied. So let's come to the problem. So they have stated that at initial estimation of the users, these are the 2.5 users gets infected in the secondary infections, right? And after giving some vaccine, they have provided the vaccination to the user, to the people, and after giving the vaccination, they increase their immunity to tackle or to address that uh, to defend that particular virus, right? Then the reproductive number after giving the immunity, after giving the vaccination, the reproductive number again calculated, means we have a probability right now 0.5, 0.7. Based on that, we are getting as an r0 is equal to, which is an expected number of users get infected, which is an 2.5, right? After some period of time, they have given a vaccination to these networks, vaccination, right? Vaccination to the network. Then the probability to get this user is very less than, that is in 3.3. Let's I'm taking random numbers here, only to I need to understand uh, how to what is the basic of this, means after giving the vaccination how the probability gets reduced, and what is the impact on that particular reproductive number, that we need to understand here, right? Then we have again calculated the reproductive number and we got as an point 1.8. Correct. I hope you have understood this scenario, the question scenario, yeah, here. So, so how we can calculate? Anyone want to add something? How we can calculate the percentage of immunity provided by the vaccine? How many users has get uh, infected? Means recovered from this vaccination? Anyone? Okay. So here, how what we need to do? Firstly, we need to find out um, how many from so 1.8 out of 2.5, how many has an still infected, still has an not recorded, not immunely record this virus, actually this disease actually. So let's take a second. So yeah, so we are getting as an 0.72, right? So these 0.72 as an gets still has an infection. They have not recovered. They have not immune. Okay. So immune, they have not get vaccine. We can say that, and those people has an still in disease. We need to find out that uh, how many gets immune, right? So for that we need to take 1 minus 0.72, right? So this will give those many users or those many percentage gets immunity. It means those many users has gets immunity, right? So from this we are getting an point 0.8, 0.28, which is an 28 percentage, right? So the option 2 is correct here. I hope this is understood. It's very simple how we have calculated, right? Yeah, firstly, we have taken out of which estimated number how many has recovered, means how many has infected, right? So we found that 0.72 still in infected, 0.72% users are still infected. We want that those users, the number of percentage, um, those users who has recovered or who has gets immunity, right? So we have minus, or we have uh, from one, that is an total number of infected users still has an infection. So from this we are getting directly 0.28, which is an 28 percentage users gets an immunity, right? Yeah, let's move to the another question. Which of the following is correct if the basic reproductive number is less than 1? Yeah, already discussed while discussing the previous questions. So anyone want to answer this question? If it is wrong, it's still fine. Okay. Anyone? Anyone want to answer this question? Okay. As we have saw that uh, how the basic reproductive number is calculated, means what is basic reproductive number, that we have saw, that is a secondary infection number which represents, right? And so we have represented a basic representative number which is an R0, which is an K into P. K is the number of children that all the users has in the have an in that particular tree network. P is an probability to get user infected, right? That age probability, simply we can say that. Okay. So if they are saying if R0 is less than 1, so what do you mean by R0 is less than 1? If it is greater than 1, then we are saying that these many users are infected, right? This R0 represents what is the meaning of this R0? That's a basic reproductive number, but what exactly it states actually means, it is stating that from a particular node, from particular user, how many user gets in the secondary infection, how many users get, expected number of users get infected, how many expected number of users get infected. So if it is less than 1, then there, that means is that there is a no one has infected. No one means, if it is greater than 1, we can say that at least one user has been had get infected. If it is 2.5, then two users are infected. 1.2, that is an one user has expected number is one user gets infected likewise. So while explaining this, you might get the one conclusion that less than 1 r0 values is less than 1. uh, it represents that there is a no expected users gets infection. There is a no as such users are there. Those users are infected. Okay. And the r0 greater than 1, that means there is an some in some expected users are there to get infected, right? They got infections. So if it is less than 1, then there is a no disease will be persist. No disease will be persist in the network. They are dies away actually. So they are dies in the first primary section. If it is greater than 1, there is an chances to get disease persist with the probability. So let's answer this question. So I have given overall idea what exactly less than 1 means, what exactly basic reproductive number greater than 1 means, what we can conclude based on this uh, scenario. Okay. So let's see the first question. What it states that the disease dies away with a probability 0. So the disease dies away. That is true. That is fine. The disease will be dies away because that reproductive number. Sorry, that reproductive number is less than 1. But with the probability 0, it is stating that it dies away, but probability of dying the disease is 0. It's not like that. If it is dying the disease, then the probability greater than the 0, right? There must be the probability greater than 0 to die the particular disease in the network. So this statement is not correct. Let's come to the second statement. The disease dies away with probability less than 1. As we know that the probability will range in from the 0 to 1 actually, right? It's a less than 1, that we know that is an might be point 2, point 5, but that is an sure thing we are getting here. Sure thing we What sure thing we are getting here? There is a no that disease will dies away. uh, it's confirmly we are saying that because that is a no users get infected here, right? There is expected I will write here 0. Expected users infected 0. So this is and not true. This is also not true. It partially true, but it can't directly we can say less than 1. We need to because we are if it is point time in this scenario, there might be case that the probability will be the disease dies away with the probability zero point 0.9. In this scenario it comes this condition, but that is not a scenario here. You can see expected user infected is 0, then there is a no disease, there is a no disease persist in the network. It is directly 0. Directly means there is a no disease, so disease dies away, which is a probability with 1. You can see the disease dies away with probability 1. That is correct. This is correct. The disease persist with the probability. This is not correct. It is not persisting. The network we have 0, so the disease not persist in the network. It dies away with the probability 1. So that's why the option 3 is correct here. Okay. Yeah. Anyone want to answer this question? This is very simple also. This is a theoretical question. So if you understood what exactly the spread of contagion means, the spread of the disease, so you can easily answer this question. Is anyone? Please try to understand what exactly the question is asking. Okay, it's very theoretical. It's not like need to calculate anything or select the factors that affect the spread of contagion, spread of the disease, the density of the contact network. It's not any contact network, density of the contact network. Okay, degree of contagiousness means how that uh, contagion or rate of spread, how fastly, how quickly that particular disease spread in the network. Let's see in the, as compared to, suppose it is an HIV disease, and with the comparative with the COVID-19, that intensity or the rate of the disease is spreading, the yes, COVID-19 is very high as compared to the HIV, right? So if it is only contacted by a distance in a particular distance, if the two users are contacted or has comes together in a particular distance, within a distance, then they gets a infection in COVID-19, COVID, right? The HIV is not like that. There is an the connections, the connection is very uh, sparse. We can say that, but in in like this question, in like this disease, there is an mm, that the virus gets an infected very fast rate, right? So the degree of contagiousness that states like that means it is stating that how the rate, how much rate the disease gets spread actually, right? That is a degree of contagiousness. That is correct. Another is in both the density of the network and contact network. It is also true that the first statement states that how much the network is densely connected, right? If it is only like this connected, like this way, suppose, second, if it is connected like this way, oh, so and if it is connected, then there is an uh, spread of contagion is very affected actually in this compared to this network and this network. Okay, so this network and this network, the contagion, the affection of the contagion will be affected by these two networks. So this two is corrected, but the statement three has on both. It requires the both impact of the both will be required. It's the density of the network and the degree of contagiousness. How, what is the rate, or how fast, how quickly the virus gets infected. That is two important factors, or factors will be affected to the spread of contagion. So the here option um, three is correct. Instead, these two options, right? In a city, let's jump on the another question. In a city, an infection TOC, there is a virus that is related to the RNA, uh, the Toro virus or something like that. It's let's take an, if it not understood the this TOV virus. Let's take a one virus that is uh, one that is one virus which is found to persist with the probability p is greater than zero, right? Right. So it is giving the probability of persist, this disease persist in the network is greater than zero. That means our basic reproductive number R0 is greater than 1. right? There is some expected numbers of infected users are there. Which of the following is are the possible reproductive number? I have already given the answer here actually. So what do you think, which options are correct here? Yes, anyone? I already given the answer while explaining the scenario, while explaining the question. Yes, anyone? Which options are correct or which single option is correct here? Right. Yes, anyone? So I have written the answer as well here. Reproductive number is greater than. So the clearly it states that the probability of a virus persist in the network is greater than zero. That means there are some users are there which are infected by this particular TOV virus. That means our reproductive number R0, basic reproductive number, is greater than 1. As we saw that in the previous example, while discussing the previous example, reproductive number less than 1, that means there is an no one has been infected. There is expected number of users infected gets infected is 0. That means the disease died away, the probability of disease died away is equal to 1, and the probability of virus persists in the network in that scenario is 0, right? So here there is no calculations are there. The values are only given. That is some confusion for confusion, but it is a very straightforward the question and answer as well. So as I have already written the statement here, that is R0 reproductive numbers, and they are asking the which of the following is are the possible reproductive numbers. The possible reproductive, this is not possible, right? It is less than this R0 value. These are the R0 values actually. Okay, these are the less than value. This is not possible because our virus is persistent in our network. So only these values are possible which are greater than 1, that I have already stated here, right? So option 2, 3, 4, these three options are correct. Let's move to another question. If you have any doubts, please let me know. Okay? In which of the following model does node V becomes infected during the epidemic? Infected during the epidemic, if and only if there is a path to V from one of the initial infected nodes that consist entirely of open niches. So it is stating that V gets infected during the epidemic if and only if from one of the initial infected nodes. So there is an initial node is there. From that particular initial node there is some path is there, and from this path this vgate node is infected like this. This is an initial node infected infected likewise. So this scenario where we have seen this scenario, that from the initial node we are getting a path to infected node for each of the infected node from initial node. So we saw a SIR model, SIS model in while discussing the last question, previously questions. Okay, so in that we does not saw a particular path from the newly infected users and the initial user, right? The initial users in the SIR and SIS model gets recovered or gets susceptible again, right? In SIRS, so there is a no path consist in the uh, modeling, while modeling the epidemic. Further, in this week lecture, we have shown a percolation model, percolation process actually, right? And yes, yeah, this is not we have shown. It's not actually related. It's, and for confusing, it is giving a one term actually. So percolation, we have so in SIR and SAS, we model the epidemic in dynamic way. That is, in T1 or day one, this node is infected, and at day two, this node gets infected to other nodes, and this particular initial node gets again recovered. Then it goes to the recovered state. Likewise, after that, this is implemented or running on the time basis. But in the percolation, it is implemented on a static network. Static network. So we have a node, we have a network, and for each of the age, so for each of the age, we have given there a decision. Means that is, in suppose E1, E2, E3, E4, E5, right? And we have E1 is equal to some decision already we have, that is pre-computed in this decision. Means while modeling the epidemic modeling, prior of that modeling, we have tossed for each of the ages, we have tossed a coin, fair coin, and we have a result of that particular tossed coins, that is a head or tail. So the E2 has an tail, E3 has an head, E4 has an tail, likewise. So, and we have a set assumption that if any age has an uh, head gets as an head, then those users, those particular age are enabled to infect the users. Okay, infect. So for the assumption, we have taken only a few labels of these ages. Okay, so here E1 is get infected, so this node get infected. Firstly, this initial node gets infected. Likewise, E2 tells that E2 age has an tail. That's why it is not infected, because we are infected the node which has age with the head. Okay, E3 infected this node. Likewise, likewise. So you can observe here there is an a path persist in the network here, right here. So we can and there is here the node is here, that is not connected with any age which has an um, head decision, head result, right? So that's why it is not infected. But you can see other nodes as infected. This is a static node, it's not time variant. Okay, so we can find for each node path from the initial node. You can see here. That's why this uh, this process has been explained, which is related to the percolation model, percolation process. This option is correct. So whatever I explained, that is modeling of the percolation. Okay. Let's see the last question. Given that the reproductive number of an epidemic in action is zero point 0.5, what are valid attempts to curb the disease? Right? Given that reproductive number of epidemic is in zero point 0.5, so the reproductive number R0 is in zero point 0.5 has been given here. What are the valid attempts to curb the disease? Okay. So here isolate the infected person so that reduce the number of people. So what do you think, which option is correct here? Anyone? Okay. So the option three, it states that create awareness among the population or population to follow proper hygiene, thereby reducing the probability of disease spread. You can never curb the spread of this disease. The disease dies away even without intervention. Right. Because you can see this R0 gives an point 0.5. That means that R0 gives an secondary infected users. That is an expected number of users. Those are infected. Right. So that is an point 0.5, which is less than R0 less than 1. That means the probability of disease persist persist in network is 1 is 0, and the probability of disease dies away is equal to 1. That means there is no one is infected, no one is infected by using this uh, reproductive number. If it is reproductive number is this point 5, which has been given in the question, then there is no epidemic has been happen in this network. No one has been infected. So the option C, option 4, you can see the here the disease dies away even without intervention. There is no intervention is required. Disease already dies away because the R0 reproductive number of for the epidemic action is 9.5. Okay, yeah. So option 4 is correct here. Yeah, I hope you uh, understood the questions and their solutions. And while discussing the question, we have also recall the particular concepts such as SIS, SIR model, percolation model, what is a reproductive number, how the reproductive number we can analyze that, right? Based on that, the reproductive number, how we can comment on the network, how we can comment, how we can comment on the spreading of the disease. Actually, it is persist in the network or it is not persist in the network, right? It is dies away or not based on the reproductive number, right? Yeah, I hope you have understood. Yeah, if you have any doubts, okay. If not, you can leave the meeting then. Thank you. Thank you for joining this meeting. Let's meet in the next week, Friday. Thank you.